Good day everyone. I'm here to present my video presentation about Completely Fair Scheduler. So first, CFS overview. CFS stands for Completely Fair Scheduler and is the new desktop process scheduler implemented by Ingo Molnar and merged in Linux 2.6.23. It is the replacement for the previous vanilla scheduler's sched other interactivity code. Second, ideal multitasking CPU is a non-existent CPU that has 100% physical power and which can run each task at precise equal speed. In parallel, each 1 per NR running speed. For example, if there are two tasks running, then it runs each at 50% physical power, for example, actually in parallel. And then last, on real hardware, we can run only a single task at once. So we have to introduce the concept of virtual runtime. The virtual runtime of a task specifies when its next time slice would start execution on the ideal multitasking CPU described above. In practice, the virtual runtime of a task is its actual runtime normalized to the total number of running tasks. Next slide. CFS, or Completely Fair Process Scheduling in Linux. First, Linux takes a modular approach to a processor scheduling in that different algorithms can be used to schedule different process types. A scheduling class specifies which scheduling the policy applies to which type of process. Completely Fair Scheduling, or CFS, which became part of the Linux 2.6.23 kernel in 2007, is the scheduling class for normal or as opposed to real-time process and therefore is named sched normal. And last, CFS is geared for the interactive application typical in a desktop environment, but it can be configured as sched batch to favor batch workloads common, for example, on a high volume web server. In any case, CFS break us dramatically with what might be called classic preemptive scheduling. Also, the completely fair claim has to be seen with a technical eye, otherwise, the claim might seem like an empty boast. Classic preemptive scheduling versus CFS. First, Unix popularized classic preemptive scheduling, which other operating systems include Box or BMS, Windows NT, and Linux later adopted. At the center of this scheduling model is a fixed time slice the amount of time, for example 50 ms, that a task is allowed to hold a processor until preempted favor of some other task. If a preempted process has not finished its work, the process must be rescheduled. This model is powerful that is support multitasking or concurrency through the processor time sharing even on the single CPU machines of yesteryear. Second, the classic model typically includes multiple scheduling queues, one per process priority. Every process in a higher priority queue gets scheduled before any process in the lower priority queue. As an example, VAX or VMS uses 32 priority queues for scheduling. Last, CFS dispenses with fixed time slices and explicit priorities. The amount of time for a given task on a processor is computed dynamically at the schedule as the scheduling context change over the system lifetime. CFS features. CFS supports symmetrical multiprocessing or SMP in which any process, whether kernel or user, can execute on any processor. Yet configurable scheduling domains can be used to group processors for load balancing or even segregation. If several processors share the same scheduling policy, then load balancing among them is an option. If a particular processor has a scheduling policy different from the others, then this processor would be segregated from the others with respect to scheduling. Second, configurable scheduling groups are another CFS feature. As an example, consider the NGINX web server that's running on my desktop machine. At startup, this server has a master process and four worker processes, which as which act as HTTP request handlers. And last, the particular worker that handles the request is irrelevant. It matters only that the request is handled in a timely manner. And so the four workers together provide a pool from which to draw a task handler as requests come in. And CFS implementation. CFS requires efficient data structures to track task information and high performance code to generate the schedules. Let's begin with the central term in scheduling, the run queue. This is a data structure that represents a timeline for a scheduled task. Despite the name, the run queue need not be implemented in the traditional way, as a FIFO list. CFS breaks with tradition by using a time-ordered red-black tree as a run queue. The data structure is well suited for the job because it is a self-balancing binary search tree with efficient insert and remove operation that executes in O log n time, where n is the number of nodes in the tree. Also, a tree is an excellent data structure for organizing entitled entities into a hierarchy based on a particular property, in this case of vruntime. Second, in CFS, the tree's internal nodes represent tasks to be scheduled, and the tree as a whole, like run queue, represents the timeline for task execution. Red-black trees are wide used beyond scheduling. For example, Java uses this data structure to implement its tree map. And last, under CFS, every processor has a specific run queue of tasks, and no task occurs at the same time in more than one run queue. Each run queue is a red-black tree. The tree's internal nodes represent tasks or task group, and these nodes are indexed by their vruntime values so that, or in the tree as a whole or in any subtree, the internal nodes to the left have lower vruntime values than the ones to the right. So in this picture, we have a 25 double hash 25 is a task vruntime. 7 followed by 17 to 29, 17 roots the left subtree and 29 in the right one. 519 and so on, and nil leaf nodes are nil. In summary, tasks with the lowest vruntime and therefore the greatest need processor somewhere in the left subtree, tasks with relatively vruntimes congregate in the right subtree. Preempted tasks would go into the right subtree, this thus giving other tasks a chance to move leftward in the tree. A task with the smallest vruntime wins up in the tree leftmost internal nodes, which is thus the front of the run queue. So this is the image in the summary. Okay, CFS illustrate how a straightforward idea, given every task a fast share of processor resources, can be implemented a low, fast, but highly efficient way. It's worth repeating that CFS achieves fast and efficient rescheduling without traditional artifacts such as fixed time slices and explicit task priorities. The pursuit of even better schedulers goes on, of course. For the moment, however, CFS is as good as it gets for general purpose processor scheduling. And that's all. Thank you, God bless, and stay safe.